Okay, so let's use what we did last time to evaluate this integral right here. So remember last time we were able to express this thing in terms of an angle by looking at a right triangle like this. Okay, so let's do the same thing here. We see this expression here, and if you tried to do any amount of u substitution here without this, well, I'm not going to say it's impossible, but it would not be pretty, even if it was. So let's go ahead and remind ourselves that, well, since we have this sort of form right here, the substitution I would like to make will look like this. Okay, so I'm going to begin by thinking about a right triangle where this side is my expression, my strange radical expression. This side is my x and this side is my 1. Okay, and now, given that that's theta, I can read off all of my translations into terms of theta and then substitute them in here. Okay, so I don't need this paper anymore. I only wanted it to remind you how we should label the sides. Where should I put the x? Where should I put the L? Where should I put our constant, in this case, A is 1. So looking at our triangle right here, what I'm actually saying is to let sine theta equal my x right here. And therefore, if I try to make a du type of substitution, I will need to take the derivative of this. So cosine theta d theta will equal dx. And for my radical expression, this is the main reason that we're doing this, that will equal cosine of theta, because I can see adjacent over hypotenuse. Like this. Okay, so that will allow me to complete all my substitutions here. So using that information, we're going to see our dx become a cosine theta d theta. There. We're going to see x squared become sine squared. And we're going to see this radical become cosine theta. Okay, so this is exactly what allowed us to complete this step here. All right, now we can go on and evaluate this integral like normal. The cosines will cancel, and I'll have 1 over sine. 1 over sine is the same as cosecant, right? So this is cosecant, cosecant squared theta d theta. Remember, always take a step to simplify and rearrange things to plan your next attack. So I did this in order to decide on what my next attack was. If you remember, the derivative of tangent is secant squared. And so in the same way, the derivative of cotangent is minus cosecant squared. So we're off by a minus sign, but that's fine. We'll have it right here. So I can say it, a couple of ways. The derivative with respect to theta of cotangent of theta is minus cosecant. I think this is the one that most people memorize, and so I'll state it that way instead of an integral. Okay, so now we have cotangent of theta plus c, all right? And I need to turn back into x to get my final solution here. So cotangent of theta is 1 over tangent theta, and tangent is the opposite over the adjacent. So this guy should be adjacent over the opposite side, okay? So that means, looking at my expression here, the adjacent side is this. Looking at my triangle, I mean, the adjacent side is this, and the opposite side is this. Okay, so this is because cotangent theta is equal to the adjacent side of my angle over the opposite side. And that's our expression. I would recommend you take the derivative of this and check that you get the original expression if you are skeptical that this is what worked here. So the next thing we have to do is pay a little closer attention to what we actually did here. I'm going to want to see this in your work. All this here has to be present in your work. Okay, I'm going to need to see justifications like this as well. Okay. Now we're actually going to have to go and dig a little bit deeper into what's going on here with this substitution. So I'm going to take another video in order to discuss that.